As you may realize by now, the class of stochastic processes is enormous. In fact, there are far too many processes with strange behaviors in that class for us to consider all of them. So to avoid dealing with all of them at once, we want to narrow down a class of stochastic processes to somewhat more manageable size. And we want processes that are easy to work with and of course relevant for engineering. One property that is frequently assumed in engineering and science is that systems are independent in some sense of the choice of reference time. And this is often referred to that the system is time-invariant. This is an assumption often imposed. And therefore we actually come to the idea that, or the first idea we will explore here, is to consider only processes where, loosely speaking, all CDFs don't change if the time has shifted. To illustrate what we mean here, if we look at a process x of t, so this could have some realization like so, could be more of these. At some point in time, t1, we have a random variable t1, and what we want to have is that if we shift this time by some amount tau, say, so we consider instead the stochastic variable that you would get out here when you cut down at this time, so that would be x of t1 plus tau. So in this case what we want is to have the probability, or the CDF, for x at t1 less than x1, say. This here should be independent of a time shift, so we want to be able to shift the time x t1 plus tau less than still x1, and this should be the same. So this would be the first order CDF. The CDF of the random variable you obtain by sampling the process at time 1 is the same as at time t1 plus tau. But in the full description we have all in order CDF, so at least we want to consider also the case where we have 2 times, so t1. And also this should be independent of time shift, so we would have the same but shifted in time by an amount tau. So we want this equality and this equality and actually all in order CDFs should be time invariant. So that means all the values sampled at different time t1, t2 up to tn, the CDF of all, the joint CDF of all these values should be the same as the joint CDF of the time shifted samples here. So by requiring so, we actually achieve a definition of stationarity, which is called strict-sense stationary processes. So the definition is here that we have a process x of t, and this one is strict-sense stationary if all endpoint joint CDFs are invariant under arbitrary time shifts. So this is the equality we had just before. And this should actually hold for arbitrary n, so for no matter what n should be. To show that a process is strict-sense stationary, we actually have to show that this equality holds for all, or for an arbitrary value of n. So for all endpoint joint CDF, we have to show this equality. It's hard to show that a process is strict-sense stationary because this requires access to all endpoint joint CDF, so the full characterization of a process. However, there are a few examples where we can do so. One example is the IID process. So for the IID process, according to some CDF fx here, we know that we can write up the full characterization So for arbitrary n, we have this relation here that the joint CDF is simply a product of the CDFs. And since there's no n dependency on the probability here on fx, we can just shift this by some amount. So actually this is equal to the probability of xk1 plus L being less than x1 and xkn plus L being less than xn. So this holds for arbitrary time shifts in arbitrary integer time shift, and this means that xk is strict and stationary. So now let us look at the mean, variance and covariance function of a strict and stationary process. So if we consider a strict and stationary process x, we know that the CDF x of t is actually the same as the CDF of x of t plus tau, so the time shifted CDF. So all CDFs, no matter what, is actually equal to the CDF at time 0. So this also means that the mean of x is equal to the mean at time 0. So that's a constant, so we'll just define ourselves a constant, mu x. And the same holds true for the variance. This is actually the variance at time 0 is equal to all other variances, so we define a new constant, sigma x squared. So essentially we just drop the time dependency on the variance and the mean. So in fact we may go one step further to consider the joint CDF of two sample points. And we know that because it's a strict and stationary process, then by assumption this CDF here, the joint CDF, is shift invariant. So it means that this CDF is equal to that CDF where we have shifted time by an amount tau. By letting tau be minus t2, we obtain this relation here. So for a particular tau, which is minus t2, we get this CDF here, which is still equal to the CDF from before. That actually means that we can compute the covariance function for t1 and t2 just by this time shift, 0. So it actually means that the covariance function is only a function of the difference between the two times and not the two times themselves. So again, we can define a new function with the same symbol as before, and we write Cx of the time shift t1 minus t2. So Cx depends only on the time shift in this case. So these were some results of a process being strict and stationary. We get a time-independent mean, a variance, and the covariance actually gets dependent only of the time shift as we wanted. So what we have shown here is a strict and stationary process. So if x of t is strict and stationary, it means that the expected value or the mean is constant, the variance is constant, and the covariance function is only a function of the time shift in between two sample points. We may consider now the question, is the opposite true? So is it true that these conditions, let's call them star. So is it true that star actually implies strict and stationarity? And the answer to that is no. No way. This does not hold this way. It's not true. And one example that would show that, it's easy to come with counterexamples, but to do so we would need a process which has constant mean, constant variance, and a covariance function that only depends on time shift, but do not have constant CDFs as required in strict stationarity. So in fact, what we can do is to give an example, a counter example. So this is a non-strict stationary process that actually has a constant mean and covariance that only depends on time shift. We construct this process by taking x of k to be independent samples, not identically distributed. That would be an IID process, which we know is strict and stationary. But we take, for every odd time value k, so for 1, 3, 5, etc., we take x to be a uniform random variable between minus square root 3 and plus square root 3. So this gives us a variable with a mean 0 because it's centered around 0 and variance 1. And at all even time steps, so 0, 2, 4, etc., we take just a Gaussian random variable with 0 mean and variance 1, so the same mean and variance as up here. So if we compute the means for any k, we get 0. So if k is odd, we get the mean of this, it's 0. If k is even, we get the mean of that, it's still 0. And if we compute a covariance, because they are independent and have 0 mean, we know that whenever k1 is different from k2, we get 0. And in the case they're the same, we just get a 1, so that is the variance from this one or that one. We may actually write this up as in the form where we use a Kronecker delta. So Kronecker's delta, which is 1 if the argument here is 0, and it's 0 if the argument is anything else but 0. So it actually fulfills these conditions from before. So it fulfills these conditions here. But x is clearly not strict and stationary because even the first order CDFs differ. So this is an example of a non-strict and stationary process that actually fulfills these conditions on the first and second moment, that is on the mean and covariance function. So what we have actually looked at now is we have a whole class, so all possible stochastic processes, and we have defined some family or some group class of processes which are called strict and stationary processes. We have also realized that there is, so for all of these processes here, we know that the mean and the mean is constant and the covariance only depend on time shift. But we also know that there exists a larger class of processes where constant mean and shift invariant covariance function. So we also know that there exists this larger class of processes which are not strict and stationary but has some of the same properties as the strict and stationary processes. And then there's a super large class of processes outside which has none of these properties. But actually, in some cases we would like to work with strict and stationary processes, but we could also consider working with this larger class, and this is what we will look at when we come to weak sense stationary. So essentially these processes here would be weakly stationary processes. So WSS. This we will look at in a later video.